this is Calculus 12, Chapter 4.3. We're going to be looking at using the first derivative and the second derivative to graph the function f. Theorem 4. This is the first derivative test. And it's important to make a distinction between positive and negative y values versus increasing and decreasing functions. Just because a y value is positive does not make the function increasing. And just because a y value is negative doesn't make it decreasing. It's whether the slope is going up or down that makes it increasing or decreasing. Okay, so the first derivative test.
This is important.
At a critical point C, if f prime is greater than 0, so you want to think of this as positive. So something greater than 0 is positive, or this actually means increasing. For x less than c, and it's better to think of this as left of c, and f prime is less than 0, so negative or decreasing. Okay, so it's the derivative, not the f values. For x greater than c, so right of c. Then f has a local max at c. And f prime of c can equal 0 or does not exist. Okay, just to say this more smoothly, so if it's increasing on the left and decreasing on the right, then f has a local max at c. And for this one, we'll just say it in plain English. If it's decreasing on the left and increasing on the right, then f has a local min at c. And again, we have f prime of c equals 0 or does not exist. If the derivative does not change sign at c, then f has no local extreme at c. Okay, so if it's increasing on the left and it's increasing on the right, then there's no local extrema. So if we have a closed interval at the left endpoint of a, if decreasing for x greater than a, so to the right of a, then f has a local max at a. And then we can flip this around. If f prime is greater than 0, so increasing to the right of a, then f has a local min at a. And at the right endpoint, if it's increasing to the left, then f has a local max at b. And if we flip this around, if f prime is less than 0, so decreasing on the left, then it has a local min at b. Okay, so if it's decreasing to that endpoint, it's going to be a minimum. Concavity. So in pre-calc 12, we said that a graph is concave up if it opens up on an interval. We have a different definition in calculus. The graph of a differentiable function y equals f of x is concave up on an open interval if the derivative is increasing on I. And B, it's concave down on an open interval I if the derivative is decreasing on I. Note that we are talking about the derivative increasing or decreasing, rather than previously we had been talking about the function increasing or decreasing. And we have a concavity test. The graph of a twice differentiable function y equals f of x is concave up on any interval where the second derivative is positive. And concave down on any interval where the second derivative is negative. Okay, so if we have positive and negative, then we must have zeros. So the point of inflection is a point on a graph where the second derivative changes sign. Okay, so the concavity changes, so from positive to negative, or negative to positive. For example, the second derivative here is negative, so that's concave down. We have another inflection point here, and this, the second derivative is greater than 0, so this is concave up. Here the second derivative does not exist, and here we have the second derivative is less than 0, so that's concave down. Here we have the second derivative does not exist. The second derivative is positive, so this is concave up. And we have another inflection point here. Concave up, concave down. Second derivative is positive, second derivative is negative. Theorem 5, this is a second derivative test for local extrema. So if the first derivative equals 0 and the second derivative is negative, then f has a local max at x equals c. If the first derivative is 0 at c and the second derivative is positive at c, then it has a local min at x equals c. Okay, so we plotted our inflection points in the previous one. So y double prime is less than 0. Y double prime is greater than 0. Y double prime is less than 0. Y double prime is greater than 0. Inflection point. Y double prime greater than 0. Y double prime less than 0. Okay, here we have f prime of c equals 0. This is a max because we have the second derivative is less than 0. Here, first derivative equals 0, and this is a min. Here we have a max, but we have to use the first derivative test because there is no second derivative. It does not exist. Here, f prime of c equals 0, and this is a min. Again, here's another max, and it's the first derivative test. Here, f prime of c equals 0. F double prime of c equals 0. So that doesn't tell us whether we have a maximum or a minimum. We can't say. And the first derivative test also says no extrema because it's negative, negative. It has to do a sign change in order to be a minimum or maximum. Okay, here's another type of question. So you're supposed to find f from the first derivative and the second derivative. A function f is continuous on its domain, closed, -2 to 4. We're told that f of -2 equals 5, so we should plot that right away. F of -2 is 5. F of 4 equals 1. And the first derivative and second derivative have the following properties. From -2 to 0, we have increasing and concave up. At 0, it does not exist, so this must mean it's a corner. So let's just put this down. Starting points. So just plot them. This tells us we have an inflection point. Okay, we're not told where the point is at 0, so we can just basically put it anywhere. So as long as it's concave up and increasing, we can put it there. Concave up and increasing. So from 0 to 2, we have decreasing and concave up. And at 2, we have an inflection point, so we can just put that inflection point anywhere. I'll just go here. Concave up, decreasing, and we have inflection point. And now we have decreasing and concave down. Okay, so concave down and decreasing. This is an absolute max. This is an absolute min. This is a local min. Okay, it doesn't ask for a local min, but it asks for absolute extrema. And we found the inflection point and we sketched the possible graph. Okay, so it's important to note this was not a fixed point or starting point. So we could have drawn it up here, we could have drawn it here. Again, the inflection point, it's not specified, so it could have been anywhere from here to here. It has to be between this point and this point. Can't be anywhere else, can't go above. Otherwise we would have increasing, and it tells us that we need decreasing and decreasing. Okay, so this is a graph example. We need to graph a polynomial. So we need to take the derivative, take the second derivative. We need to find intercepts, x-intercepts. We need to find critical points. And we need to find inflection points. And we also need to find the y-intercept. With a polynomial, it's easy. It's just a constant term. With the x-intercepts, this is not easily factorable. So we'll just use a calculator to solve for that. Enter our function, x raised to the power of 4 divided by 4 plus x cubed minus x squared divided by 2 minus 3x plus 2. And draw. And we're going to do the solutions. We're going to find the roots or x-intercepts or zeros, depending on what your calculator says. So the first one is approximately negative 3.236. Negative 3.236. The next one, negative 2.732. And the next one, 0.732. And the last one, 1.236. And for the critical points, we're solving the first derivative equals 0. This is a cubic function. This is a nice function, so we can use the factor property. We try the easy number first, plus 1, and we get 0, so it works. We do our synthetic division. This gives us a quadratic, and we can just factor that normally. So we have these 3 factors, which means we have x equals plus or minus 1 and negative 3 as our critical points. For our inflection points, we solve the second derivative equal to 0. This is not a nice quadratic, so you need to use a quadratic formula. You can use exact values, but I'm just going to use an approximation. It's approximately negative 1 plus or minus. This is almost 49, so we can say square root 49, that's 7 over 6. So we have negative 13 over 6, and we have 1/6. Okay, y is generally concave up because it's a quartic function and it opens up. And algebraically, because a is greater than 0. That means no absolute or global max. Because it opens up, it's going to go to positive infinity. If we have a continuous function, we know the maximum and minimums will alternate. If there are holes or jumps, then we could get a max followed by another max. But since a polynomial is continuous, we can conclude, so x equals negative 3 and x equals 1 are local mins, and x equals negative 1 is a local max. Okay, let's find these maximums and minimums. Y of negative 3 equals, we can just use our calculator here. Otherwise, if you're not allowed to use a calculator, you have to figure it out by hand. We can trace negative 3, and we get negative 1/4. Y of 1 equals negative 1/4. Y of negative 1, 3 3/4. Or you can say 12 plus 3 is 15 over 4. We now know that these are our absolute min, and this is still just a local max. Okay, we should prove that these are mins and maxes. So we need to do the first derivative test or a second derivative test. So if we do first derivative test, we have y prime. We need a value to the left, and I would pick integer values, negative 4. We need an integer value between these two, that's negative 2. And an integer value between these two, that would be 0. And an integer value to the right, 2. Okay, 0 is easy. It's just a constant term, negative 3. And this is less than 0. So we should find something greater than 0, and less than 0. Okay, we can just use our calculator to do this for us. Exit. Let's enter the first derivative, x cubed plus 3x squared minus x minus 3. And we're going to trace. We're going to go to the second function because it's on the first function right now. Negative 4. That's negative 15. Negative 2. That's 3. and 2. That's 15. That confirms it. We have negative, positive, negative, positive. We can do a second derivative test. Y double prime. So we just use these values. Negative 3, negative 1, and 1. We'll enter that one on the calculator too. 3x squared plus 6x minus 1. Trace, go to the third function, put in negative 3. That's 8. That's greater than 0. Negative 1. Negative 4. That's less than 0. 1. That's 8. That's greater than 0. Okay, we're not concerned about the value as much as whether it's positive or negative. Again, this is concave up, so this is a minimum. Concave down, this is a maximum. Concave up, this is a minimum. Now we can go ahead and plot. We'll start with our minimums and maximums because those are easy values. So we have negative 3 and negative 1/4. We have negative 1, and that's 3 3/4. We have 1, and that's negative 1/4. We have a y-intercept of 2. We have inflection points. I'm going to do that in a different color. We have negative 13 over 6, so that's roughly here. That's just a little less than negative 2. So that should be somewhere between these two values. And we have an inflection point at 1/6. So that's going to be roughly here. We'll move this dot just a little bit. Okay, now we can draw our curve. These x-intercepts are pretty close to the min. So we'll use green for our intervals of increase and decrease. So we have negative 3, negative 1, and 1. Just put a circle around that. Okay, so we have a decrease, increase, decrease, increase. Or you can say f prime is less than 0, f prime is greater than 0, f prime is less than 0, f prime greater than 0. Okay, let's do our concavity. We have a point there and a point there. This is approximately negative 13 over 6, approximately 1/6. And we have concave up. That's f double prime greater than 0. Concave down, f double prime less than 0. Concave up, f double prime greater than 0. And we should label our points as much as we can. 0, 2, 1, and negative 1/4. Negative 3 and negative 1/4. These are absolute min. And here is our local max. And that's negative 1 and 15 over 4. And we should label our inflection points. Approximately 1/6. We need our original function again, so 1 divided by 6. It's approximately 1.49. And this one, inflection point, negative 13 over 6, approximately again 1.49. So the warning here is the second derivative test may fail if the second derivative is 0 or does not exist for determining extrema. So use the first derivative test instead. For example, if we have f of x equals x to the power 4, the first derivative is 4x cubed, the second derivative is 12x squared. The first derivative is 0 at 0, second derivative is 0 at 0. So this doesn't tell us whether it's concave up or down, so we don't know if it's a minimum or a maximum. However, if we do the first derivative test, we pick a point to the left, negative 1. That gives us negative 4. And we pick a point to the right, 1, and the derivative is 4. Because it's decreasing and then increasing, f of 0 is a minimum. And you should
recall
that if the second derivative is hard to do, stick with the first derivative test. So the second derivative will be hard to do if your first derivative involves a quotient. So you might not want to do a second derivative test. And that completes this lesson.